All right, so welcome everyone. The purpose of this video is to introduce a couple of concepts. The first being what a moment is, and the second being what a moment generating function is. And so in addition to those two definitions, we will also work with a couple of different moment generating functions just to get a feel for what they really are. And so we're in our section 4 note packet now, and I'm scrolling down to the second page, down to the definition of a moment. And so we've actually used at least two moments quite often throughout the semester. So you could see the general definition of the kth moment written here. In particular, the ones that we have used are the first moment. And so M1 is the expected value of y to the first power, which is just the expectation of y. And so the first moment for a random variable is actually just its mean. We've also used the second moment, so that would be the expectation of y squared. This isn't the variance directly, but we've calculated this a lot to actually calculate the variance. So we've used the expectation of y squared also quite a bit, but it doesn't have to stop there. So k can be any integer. So the third moment would just be the expectation of y cubed. We haven't really used this, but this is it can be used to define the skewness of a distribution. So we haven't used it, and we aren't going to use it too much, but you could keep going and find the fourth moment, the fifth moment, etc., etc. The next part of this video will move into talking about a moment generating function. And so again, the definition of a moment generating function is given here. It is a function of t. And the definition, honestly, it is quite abstract. We will get some practice with this, especially in class. But for now, let's just jump to this example just to see what this moment generating function is going to look like for this simple probability distribution where x can just be three different values. So to find the moment generating function of x, I am just going to apply this definition directly. So it's again a function of t, and we're finding the expectation of e raised to the tx power. And it's been a little while since we've worked with discrete probability distributions, but remember to find this expectation, we're summing over all values of x. This is the expectation of a function of x, and so I'm going to put that part in first. And then we're multiplying that by each value of x's associated probability. So remember, this is a weighted expectation where the weights are the different probabilities. And so then with this table, we can just kind of essentially plug and chug from here. So the moment generating function for this is going to be e to the 3t times 0.6 plus e to the 4t times 0.3 plus e to the 6t times 0.1. And that is our moment generating function for this particular distribution. A theorem that we are going to make use of that I will just mention briefly here is that the moment generating function uniquely characterizes a distribution. What that means is that for the example that we just wrote up here, no other probability distribution can have this particular moment generating function aside from uh, from the one in this table. So it's impossible for any other distribution to have this particular moment generating function because they are unique. Coming down then to a couple of examples. What we did in the previous example was we had this kind of unknown distribution, so it's unknown in that it doesn't have a particular name, but each of the common discrete and continuous distributions that we've discussed so far have unique moment generating functions. And these unique moment generating functions are given on the table. And so I'm going to risk it for the biscuit, and I'm going to exit this and hope I can navigate my way back, and pull up our two tables. And so in the last column that I'm going to zoom in on, you'll see these MGFs. And so the game we're essentially trying to play with these next two examples is we're trying to match the moment generating function that's given to one of these distributions. And so again, looking at this, take a second to see if you could kind of match this to a moment generating function, and I'll give you a hint that it matches up with one of the discrete distribution's moment generating functions. After you take a minute, you should notice that it really looks like the binomial moment generating function. And to make that more clear, I am going to just do a quick rewrite of this and say that actually that is equal to 0.25 plus 1 minus 0.25. All of that raised to the 10th power. And that makes it more clear that this is the MGF for a binomial random variable with n equal to 10, p equal to 0.25. Now we're going to play the same game with the second example. And so again, I'm looking at this moment generating function, 1 over 2 minus e to the t. And I'm going to go back to this table of distributions. Again, I've got my continuous one and I've got my discrete one. And I'm scanning for anything that matches that pattern. On my initial scan, I'm not seeing anything too promising, so nothing really matches up directly. But I am seeing that the closest one looks like the MGF for this geometric random variable, because it's got this e to the t term in the denominator. And so that's the closest I can get, but it's not exact. And so what I'm going to do here is I'm going to multiply this moment generating function by 1. And so I'm going to multiply it by 1/2 divided by 1/2, which is equal to 1. That will give me a slightly different form. That now looks a lot closer to the MGF of a geometric random variable. It's still not exactly right, and so I'm going to take this extra step to do this, which is the exact same thing. So I've just replaced the, so I'll highlight I've just replaced this 1/2 part with 1 minus 1/2. So the same thing. And now it looks exactly like the MGF of a geometric random variable with p equals, I'll stick with 1/2, so p equals 1/2. So we'll stop there. Your quiz will give you some more practice with working with moment generating functions, and we'll talk more in class about why they might be something we can actually use.